Easiest method on earth to calculate the inverse of matrix. Okay, notice that I'm emphasizing earth because I don't know about other planets, right? But on earth, this is the easiest method. It's also called Gauss-Jordan method. Now, normally what we do is, if you have to find inverse of matrix, there's like algorithm involved where we first find like minor of matrix, right? And then we find cofactor, and then we find adjacent, right? Sorry, not adjacent, adjoint. And then we find adjoint, and then only we find inverse, right? So there's a lot of forces involved in it, and if it's more than 3 by 3, then it gets too hard. Now in such cases there's this another way called Gauss-Jordan method, which makes the task of finding inverse so easy. Now first of all, let me show you like how this method works, right? And then after that we will also discuss why this method works, and that's the most interesting part. But before going to that, if you like, if some of you don't know how this works, so I will just show that. Also before that, you need to know like the row operations on matrix. What does it mean? So what are the like uh, possible row operations on matrix, or like I mean allowed row operation on matrix? So let's say if I have a matrix A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, and let's say we also have D1, D2, D3, D4. There are basically three row operations on a matrix, right? Now the first one is you can swap rows. Right? Now let's say over here this is our row 1, row 2, row 3, row 4. Now let's say if I swap row 2 with row 4, what I will have is just A1, A2, A3, A4, D1, D2, D3, D4. Now the row 4 is in row 2, C1, C2, C3, C4, B1, B2, B3, B4. So this is like one of the three row operations on matrix, swapping the rows. Now next one is basically scaling a row. So let's say if I want to make row 3 as 4 times row 3, this is a row operation. And now how will the matrix look? So this will something like A1, A2, A3, A4, B1, B2, B3, B4, 4 times C1, 4 times C2, 4 times C3, 4 times C4, and then D1, D2, D3, D4. Now the last row operation on matrix that we can do is uh, basically adding a scaled row to another row. Now what this means is, let's say if I in row 3 I wanna add like 2 times row 1. So let's say if I want to make row 3 as row 3 plus 2 times row 1. This also comes under row operation on matrix, right? And like okay, so how this works is, so in row 3 others will be as it is, other rows will be as it is, right? A1, A2, A3, A4, B1, B2, B3, B4, D1, D2, D3, D4. Now in row 3 we will have row 3 plus 2 times row 1. So that means C1 plus our row 1 is this A1, A2, A3, A4, right? And we will just add corresponding rows. I cannot add to A2 in the row of C1, right? So C1 plus 2 times A1, C2 plus 2 times A2, C3 plus 2 times A3, C4 plus 2 times A4. So this is how this third like a row operation works. Now row operations are special because row operations can be represented by a specific matrix multiplication, which we will discuss at the end of this video, because that is also a part of the proof of why this method works and why these row operations are special, because each of the row operations have a specific matrix multiplication representation. I mean, doing a row operation is same as multiplying a matrix by another specific matrix that represents a row operation. We'll discuss that at the end, but now I guess you do have an idea about these three row operations that we have. Now about how to find inverse, right? So let's say if I want to find inverse of a matrix, let's say, first of all, let's begin with easier matrix. Let's say A is equals to 1, 2, 3, 4. Let's say we want to find its inverse. So in this Gaussian-Jordan method, what we do is, first of all, we write this matrix, give a bar, and then write a unit matrix. I mean identity matrix, right? So we write that matrix and identity matrix, right? Now we are allowed to do row operations so as to make this first matrix an identity matrix. We will do some row operations so as to make this first matrix identity matrix, right? And we should also do the same row operations on the second identity matrix as well, right? We're allowed to do row operations on first matrix, but the same row operations should be done on the second identity matrix as well. Now, after doing a few row operations, when this matrix becomes identity matrix, this Gaussian-Jordan method tells us that when this A becomes I, this I will become A inverse. And so that's how, when we finally make this identity matrix, if you look at like how this has changed, its final result will be our answer, A inverse. We'll discuss on that, why that works is this way at the end. But now we just get to know this stuff, right? So yeah, so now our only task is to, let's try to do some row operations on the first matrix to change it to identity matrix. Now for that, what I can first do is, okay, so to change it to identity matrix, what I would want to do is, I would okay, so I need this form, right? 1 0 0 1. So I would want to make it 0. I would want to make this one 0, this one 0, right? You get the idea. So what I'm going to do is, I will do row 2 will be row 2 minus 2 times row 1. We can do this, right? This is the third one. We can add a scaled row to another row. So we are basically scaling row 1 by -2 and adding to row 2. If we do that, so there will be one, first row will be as it is. Now in second row, there will be 2 minus 2 times 1, right? So I will just write this for now, and later on we will not write this. 2 minus, I'm subtracting 2 times row 1 is 1. Over here, 4 minus 2 times in row 1, there's 3 now. So there is 0 right now, minus 2 times in row 1, there is 1. And so there is 1 right now, minus 2 times, there is 0, right? So I'm just writing it to make clear for now, but later on I will not be writing these things. Okay, 1. Now, this is 1, 3. So now 2 minus 2 is just 0. That's what we wanted. Now this is 4 minus 6, right? So 4 minus 6 will be -2. 1, 0. This will also be -2, and this will just be 1, right? Yeah. Now again, we want 1 over here, right? So what we can do is, if we want to make this element 1, so what we can do is, we can scale row 2 by -1 by 2. You can multiply row 2 by -1 by 2, right? So if we do that, what will happen is, if we do that, okay, so if we do that, this will just be 1, and again -2 times -half is 1. 1 times -half is -half, right? Okay. So now last thing is, we now need to make this also 0, right? We now need to make that 3 also 0. So how can we do that? So for that, okay, what you can do is, in row 1 we can add the row 2 is scaled by -3. We can scale row 2 by -3 and then add it to row 1, right? So if we do that, what happens is, so 0 squared by -3 will be added to 1, that's just 1. Now 1 is scaled by -3 added to 3, that's 0. Again 1 is scaled by -3 and added to 1, so 1 minus 3 is -2. And then -half is scaled by -3 is just 3 half, and added to 0 is 3 half, right? Okay, looks good. Now what do we need to do now? Okay, now second row will be as it is because there is no operation on that. So now guys, do you notice that it's already in the identity matrix form, right? I guess you guys know what identity matrix is. Identity matrix is basically the matrix where the main diagonal is 1, right? The main diagonal should be 1. This is called the identity matrix. Yeah. So since now there we already have identity matrix over here, so now this thing that we have achieved on the I side, on this side, this was the side of A, this was the side of I. Now since this has transformed to I, this will have transformed to A inverse, right? That's the claim we made at the beginning, but we have still not proved it, which we will prove at the end of this video. Now this is the A inverse. So from all these operations, now we got that A inverse is -2, 3 half, 1, -half. So if you want to verify that this is in fact the A inverse, how you can verify is, so if A inverse is the inverse of A, then this should hold true, right? A inverse times A should be I, A times A inverse should also be I, right? This should hold true if A inverse is inverse of A. So let's check that if it's really inverse or not, because we cannot really believe anyone, right? We need to verify it for ourselves. So let's try to prove this. 1, 2, 3, 4 times -2, 3 half, 1, -half. Okay? Yeah. Now let's try to multiply. So I guess you guys know how to multiply, right? First of all, first row with the first column. So that will just be -2 plus, so first element with first -2 plus first second element second is 3, which is 1, right? Okay, so the first element is 1. Now this one with first row with second column, so this is 3 half minus 3 half, which is 0, right? Okay, so this is 0, sorry. So this is basically 3 half minus 3 half. Now I guess you guys know how to do again. Second row with first column, this is -4 plus 4, right? So this is -4 plus 4. Again second row with second column, so this is 3 minus 2, right? So this is 3 by 2 times 2, 3, 4 times minus f minus 2. So this is 3 minus 2. Now let's see what this result will be. This is 1, this is 0, this is 0, this is 1. So we have achieved I when we are multiplying A with A inverse, right? So since A times A inverse is I, we also need to check A inverse times A, but that will definitely be I. You can check that. So this verifies that, yeah, the thing that we have found is really the matrix inverse. Now if you want me to do one more example about 3 into 3, I'm definitely good to do that, but I'm afraid the video will be long. But anyway, let me do is, you guys can skip the video just a bit if you wanna like go to the proof, right? Yeah, so I'll just try to make it quick now because I think you have understood it. So let's say if I have a matrix 1 2 1 3 0 1 1 0 1 1 2 1 3 0 1 1 0 1. Okay, So again, the drill is the same. So first of all, I will write this matrix alongside another, which is just identity matrix 1 0 0 0 1 0 0 0 1. Now I have to try to convert this first matrix into 1 0 0 0 1 0 0 0 1, right? So that is our goal. So let's see how we do that. Now first of all, notice that I have 0 0 over here, right? So so if I have this in the second or third row, definitely I cannot make 1 over here, 1 over here, right? So this thing needs to be in the first row. Yeah, because only there it's helpful, otherwise it's not. So what I will do is we can definitely swap the rows. So I will swap row 2 with row 1. Okay. Oh wait, sorry. Okay, I will swap row 2 with row 1. If we do that, this row 2 will go at the front. But guys, you be aware that this row should also be transferred, because I have told you that it needs to be done in the both side. Now row 2 comes in the row, row 1 comes to row 2, and this is 1 0 0 and 1 1 1 0 0 1, right? Now to make this 1 0 0, what I can do is I can scale row 1 by half, right? I can scale row 1 by half. If I do that, I will just have 1 0 0 and then 0 half 0 1 3 1 1 0 0 1 1 1 0 0 1, right? Now what can I do? Okay, so okay guys, I guess you guys know that I also need to make this two zeros, right? And this should be 1, right? So to make those two zeros, what I can basically do is what I can do is, wait, why is it so small? Okay, what I can do is I can just say that row 2 should be added a negative 1 scaled multiple of row 3. What if I just do row 2 as row 2 minus row 3? Then both of these 1 will get cancelled, right? So I think that's the good strategy for this. Okay, now if I do that, this will just be, this 1 will get subtracted over here. So 1 minus 1 will just be 0. 3 minus 1 will be 2. 1 minus 1 will be 0. Wow. 1 minus 0 will be 0. 0 minus 0 will be 0. 0 minus 1 will be negative 1. Now this is 1 1 1 0 0 1. Now I can again scale row 2 by half. I can scale row 2 by half, right? If I do that, I will have 1 0 0 0 1 0 1 1 1. Also notice that I need to half the second over here as well, half the second row, and 0 0 1. Okay, now I need to make these two zeros, right? I need to make these two zeros, right? Okay guys, now I can do it in 2 steps. First of all, I can just make that row 2 being row, I think I want to operate in row 3 actually. So first of all, I can just do row 3 as row 3 minus row 2, right? If I do that, this will go to 0, right? And again, in the next step, I can again subtract row 1 as well. So I can do this in 2 steps actually, but I will just do it in a single step for now. So if I subtract both row 2 and row 1, this is just a merged row operation, right? This is just a combination of row operations. So yeah, this is definitely a row operation. Now 1 0 0 0 half 0 0 1 0 half 0 negative half. Now if I subtract that, this will become 0 because this 1 will cancel this 1, right? And then this will also become 0 because the second 1 will cancel it, and this will just remain 1 because there are just zeros in second and first row corresponding to that, and there will be negative half, and 3 half, right? So now we have finally achieved the identity matrix over here. Right now, since A has transformed to I, right? Since A has transformed to I, this I should have transformed to A inverse, right? That was our theorem, right? So that means, so for this A, our A inverse is just 0, half, 0, half, 0, negative half, and then negative, wait, let me erase this. Okay, and then negative half, 3 half. So this is our A inverse. 0, half, 0, half, 0, negative half, 3 by 2. If you wanna verify this, we can just do matrix multiplication. So let me do this. If you want me to do, so let's say 1 3 1 2 0 0 1 1 1 multiplied with 0 half 0 half 0 negative half 3 by 2, right? Okay, so let's do it. Now I guess you guys know how to do multiply. First of all, first row with first column, right? If I do that, what I will get is 1 times 0 is 0, 3 times half is 3 half, 1 times negative half is negative half. And then now we do first row with second column, right? So that will be half plus 0 minus negative half. Now first row with third column, right? So that will be 0 minus 3 half plus 3 half. Now we will do second row with first column, right? So then it will be 0 plus 0 plus 0. Now second row with second column, that will again just be 1 plus 0, sorry, that will just be 1 plus 0 plus 0. Second row with third column, that will just be 0 plus 0 plus 0. Now again, third row with third column, sorry, first column, that will just be 0 plus half minus half. Now third row with second column, that will just be half plus 0 minus half. Now third row with third column, that will just be 0 minus half plus 3 half, right? So our answer is, this is just 1 0 0 0 1 0 0 0 1, just as expected, the identity matrix. So for this A, we verified that this is definitely the A inverse, and this also says us that our operations, I mean the theorem is really working. It's really working. Now let's see how is it working, right? Now first of all, to know how it's working, first of all we need to really see that these row operations are really just some matrix multiplications. So let us see how, one by one, how these row operations are matrix multiplications, right? And then if we know that, then we will it will be easier to like prove that theorem. So first of all, let's see about the swapping rows. Okay, so let's say we have this matrix A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, D1, D2, D3, D4. Now let's say if I want to swap third row with the first row, right? If I want to swap, let's say, third row with the first row. Now for this swapping, look, okay, what kind of matrix multiplication we need to do? I want to show that there exists a matrix multiplication which does this. So if I want to swap third row and first row, what we will do is we will create a matrix of mainly zeros and ones. Now now there are 4 positions for me to write zeros and ones, right? And okay, in this first row, in whichever like column I write 1, that row will be in the first row. So if I want to bring third row to first row, I need to write 1 over here. And if I just want second row in the second row itself, so yeah, in second, okay, if I write 1 over here, second row will be in the second position. Okay, now if I want to bring first row in third positions, so in third position, if I want to bring first row, I should write 1 over here. Let's see, if I wanted to bring fourth row in this third position, I should write 1 over here and rest zeros. You get that? That will bring fourth row in third position. We'll also see how this is working. So if I want to bring first row, I should write 1 over here, so that first row will be in this third position. And in fourth position, if I want to bring fourth row, I should write 1 over here, rest zeros. Now if you want to try to multiply this, so if you multiply this with the first row, definitely except C1, all of them are going to be 0, right? Yeah, so this will just be C1. Now again, if you want to multiply this, if you want to multiply this with second row now, except C2, all of them are going to be 0, right? So you are going to get C2 over here. Now if you want to multiply this with third column, except C3, all of them are going to be 0, right? So we will get C3 over here. Now again, if you want to multiply this with fourth column, except C4, all of them are going to be 0. So this is going to be C4. You see that? So see, like depending upon like where we write the number, that row is going to come in this first position. You see that? So yeah, because we have wrote 1 in third position, so third row came in the first position. Now over here, there's 1 in second position, right? So definitely second row will come in second position. So yeah, now yeah, if you go multiplying, if you multiply this with first, only b1 will be there, right? So b1. If you multiply this, if you multiply second row with second column, except b2, all of them are going to be 0. So we will have b2 over here. Similarly, b3, b4. I guess you get the idea. Now, if you multiply third row with first column, except a1, all of them are going to be 0 again with the same like multiplication thing, a1. Again, if you multiply third row with second column, a2 will be there. Now I guess it's obvious, right? a2, a3, a4. And similarly, if you multiply this fourth row with first column, d1 will be there, right? And the same thing holds for all others. So d1, d2, d3, d4. I guess now you guys saw that how swapping row is just actually a multiplication by a matrix of zeros and ones, and the position of 1 is carefully chosen according to which row we want in the first row, which row we want in the second row, right? So according to that, we place the ones over here. So that is about swapping rows. So we saw that swapping row operations is actually equivalent to multiplying by this sort of matrix, right? Because we saw that after multiplication, exactly the third and the first rows are swapped over here. You see that? Yeah. So okay, now we now know that this row operation is a matrix multiplication by sorted matrix. Now let's see about another, scaling a row. Scaling a row, how this is also matrix multiplication. Let's say if you take this general matrix a1, a2, a3, a4, b1, b2, b3, b4, c1, c2, c3, c4. Now notice that I'm just like taking square matrices because only square matrices have inverse, right? Now let's say if I want to scale the third row, if I want to scale third row by some constant k. So what I need to do is I need to multiply this. I need to multiply this by the same sort of matrix where there will be 1 in the first row, so that the first row is in the first row itself. It's 1 in second row over here, so that second row is second row itself. Now in third row, instead of 1, I need to write k. Now the reason is now, and now I'll just write it as it. Now if we multiply, so there will be no change multiplying. If you just multiplying 1 0 0 0 with a1, b1, c1, d1, we'll just get a1 over here, and similarly a2, a3, a4, right? And if I multiply by 0 1 0 0 with this one, I'll just get b1, right? And yeah, similarly b2, b3, b4. Now over here, if I multiply 0 0 k0 with a1 b1 c1 d1, 0 times a1 is 0, 0 times b1 is 0, k times c1 will be kc1, and 0 times d1 is d1, right? So this will be kc1. Similarly, this will be kc2, this will be kc3, kc4, right? And now 0 0 0 d1, about fourth row, this will just be d1 only, right? So this will just be d1, d2, d3, d4. So you saw that this matrix actually scaled the third row by k. You see that? So similarly, you can adjust this. Let's say if you wanted to scale the second row, you could have instead made k over here and 1 over here, right? If you wanted to scale the first row, you can just write k over here. So that's how our scaling matrix is. So now we also saw that scaling a row is also equivalent to a matrix multiplication, which has like one of the like ones as k's, right? Like one of the ones in the identity matrix as k. So you got the idea why this is also a matrix multiplication by this sort of matrix, right? Okay, now the last one. Adding a scaled row to another row. Okay, now again, let's say we have this matrix a1 a2 a3 a4 b1 b2 b3 b4 c1 c2 c3 c4 d1 d2 d3 d4, right? Now let's say what I want to do is I want to make row 1 such that row 1 is equals to, let's say, 2 times row 3. In row 1 I want to add 2 times row 3. Now how do I do that? This one is also easier. So now what I need to multiply this is, okay, first of all, whatever numbers I write over here, they are basically going, this row is going to multiply this one, right? Now if I write 1 over here and 2 over here and rest zeros, what's going to happen? This will just be a1 plus 0 plus 2c1 plus 0, right? You see that a1 plus 2c1 is there. The 2 times the third row is being added to first row, right? So yeah, that's how it's work. So what you basically need to do is, so if you wanna like add some constant multiples of other rows, let's say in this case third row, so what you just need to do is in the third row write that constant number. So that constant number times this row, this is in third place, so third row is going to be added to the first row. So that it's that easy. So yeah, that's how we do it. And rest of the thing, if you wanna just let rest of the thing as it is, so second row let be in second place, like third row let it be in third place, fourth row let it be in fourth place. So yeah, that's how it works. So you saw that this row operation is also actually a matrix multiplication. So yeah, so that's why these three row operations are important, because all of them have a corresponding matrix representation. Like I mean, corresponding to them, there are some matrix to which if you multiply, the effect is same as being having done a row operation, right? Now we saw that after we do this row operation over here, now if I just multiply these two, I'm gonna get a1 plus 2c1, right? a1 plus 2c1. Similarly over here, a2 plus 2c2, a3 plus 2c3, a4 plus 2c4. Over here also I'm gonna get b1, b2, b3, b4, c1, c2, c3, c, because they have nothing interesting at all. So yeah, so you see that this was actually done by a matrix multiplication, and yeah, there exists a matrix multiplication for this row operation as well. So now that we know that all three row operations have a matrix multiplication representation, now we are completely ready to prove this theorem. Now in this theorem, what we have been doing is, first of all, we have been writing, let's say if you want to find inverse of A, we have been writing A and then bar and then I, right? Now we have been doing a bunch of row operations on A, right? So first of all, let's say x1 operation, x2 operation, a bunch of operations, and we are doing that, doing the same to I, and then when this A becomes I, we say that this becomes A inverse. That was it, right? Now, let's analyze this with our new observation that all the row operations are actually some sort of matrix multiplications, right? Now, if we know that, let's say first of all, I did some row operations which is represented by x1, right? So that means both of them will now become x1 times A. Over here also this will be x1 times I. Now let's say I did another row operation which is equivalent to x2. Now both of them will become x2 times x1 times A, right? Notice that these row operation matrix were in front. Yeah, so they were in front, right? Yeah, so they were always in front. So that means also here I am to write them in front, right? Now I did another row operation x2. Now let's say I did a bunch of row operations, let's say n row operations, after which my this first matrix became I, right? I did a bunch of row operations. After which, and I know that all these row operations are matrix multiplications, right? Of the same order or as this square matrix. Now after this bunch of row operations, this became I. So now notice that I'll write this as x1 times x3 times x2 times x, let's say this 1. I'll write this in bracket times A. So if this has become I, so that means this matrix multiplication must be A inverse, right? Because only A inverse times A is I, right? So this has an interesting conclusion that this product of the row operations that we did, like all these matrix, if you multiply them, that's exactly A inverse. That's an interesting thing, because now over here if you see that all this product is just A inverse, right? So this is just A inverse times I. So that means over here we know that anything multiplied by I is just that same thing. So this should exactly be A inverse, and that's how this Gaussian-Jordan method works. Guys, you see that? So what's happening is all these matrices that are making this AI, so these are all matrices being multiplied, and that should constitute A inverse because it's going to I. And if that's A inverse, and on the other side we just have that same A inverse times I. So yeah, so other side should become A inverse. So when this becomes I, this becomes A inverse. So that's basically the proof. So yeah, we also discussed why it works, we discussed how do we do this, and yeah, this was a bunch of a long journey, I guess you guys had a wonderful ride in this journey. I guess you guys enjoyed this, and now I think that you definitely are crystal clear on why this method works, how to use this method. And yeah, this is definitely one of the greatest manipulations to make difficult things easier, like mathematicians have been always doing. And yeah, so that's it for today. I'll come back next day with another interesting thing, and I look forward to seeing you again soon. Just enjoy the maths, guys. That's it.